Here's a short little video, everyone, to show you how to integrate products of sines and cosines, something that comes up fairly often in the work that we have to do in calculus. And before I do, I want to just remind you of something that we've done in Calculus 1, the concept of the differential of a function. Remember, we defined the differential of a function to be equal to the derivative of the function times dx. Okay, so I put down a few of them right here. The differential of the sine of x is equal to the cosine of x dx. The differential of the cosine is minus the sine of x dx. Or notice I wrote it another way, everyone. The differential of minus the cosine of x is equal to the sine of x dx. Okay, so what does this have to do with the work that we're going to do now? Well, here's some examples. Let me show you. Suppose I want to integrate, for example, the sine cube cosine squared x dx. Okay. Notice that the power of the sine is odd. Okay, the power of the sine is odd. If the power of the sine or the cosine is an odd power, this is what we do. Break one of them away, pair it with the dx, like this. Break one of the sines away. Move it to the back and pair it with the dx, like this. Okay. Notice that these two factors are right here. And they are equal to the differential of minus the cosine. So here's what I'm going to do. I'm going to rewrite my integral like this. Okay. Now, a couple things. First of all, that negative sign right there, that -1, I'm going to move it through the derivative symbol and the antiderivative symbol. I'm just going to move that right up front and just get it out of the way. Also notice that I'm now integrating not with respect to the variable x, which was the original problem. I'm actually integrating with respect to the cosine function, which means I can only have cosines under the integral symbol. So what I'll do is I'll rewrite this sine squared with the fundamental identity, 1 minus the cosine squared. Now I'm integrating with respect to the cosine function, and I have only cosines now under the integral symbol. Let's distribute the cosine squared through. And then we can just simply read them off, term by term. Okay. This would be cosine to the third of x over 3, cosine to the fifth x over 5 plus c. Okay, so when integrating products of sines and cosines, look to the powers. If the power of the sine or the cosine is odd, break one of them away and pair it with the dx in the back, and then rewrite the expression. Okay, here's another one. Get all my pens out of the way here. I consider this one. Okay. Now this time, the power of the cosine is odd. Okay, so we break one of the cosines away. Pair it with the dx, and notice that the cosine of x dx is the differential of the sine. Okay, so that tells me I'm no longer integrating with respect to x. I'm now going to integrate with respect to the sine function, which means I'm going to need to rewrite the cosine to the fourth power. I can only have cosines under the integral symbol if I'm going to sines, if I'm going to integrate with respect to the sine function. So I'm going to write cosine to the fourth as the cosine squared of x squared. And then I'm going to use the fundamental identity. Cosine squared is 1 minus the sine squared. Okay. And of course, we're going to have to expand this and multiply it by the sine squared. And then once we do, we'll be able to read everything off term by term. Okay. So we'll have sine to the third power of x over 3 and so on. I know plenty of you out there are more accustomed to doing problems with u substitution. So if you think about it this way, think of it as u squared du, where u is the sine function, u to the fourth du, u to the sixth du. It's okay to think about it like that. Okay. So once again, when you're integrating powers or products of sines and cosines, look to the exponents. If the powers are odd, break one of them away, pair it with the dx. Okay. Let's try another one. Let's try here. Okay, so we just have cosines. Power is odd. We'll break one away. Okay. Pair it with the dx, and then rewrite that combination as the differential of the sine. Okay. So now we're going to integrate with respect to the sine function. Rewrite the cosine squared as 1 minus the sine squared, and then read them off term by term. 1 d sine is the sine, minus sine squared d sine is sine to the third over 3 plus c. Okay, what do you think of that? That's not too bad, huh? Now, in this example, notice that the sine and the cosine have odd powers. So if that's the case, it's your choice. Okay, either break away one of the sines or break away one of the cosines. Not both, though. You have to make a choice. All right, so when both of the powers are odd, it's your choice which one of them you break away. I'm going to break away one of the cosines just because they're already next to the dx anyway. Just being a little on the lazy side. And so I'm going to rewrite this then as the differential of the sine function. Okay, which means I'm going to be integrating with respect to the sine, which means I'm going to have to rewrite the cosine squared with the fundamental identity. Okay, I will have to distribute these through, but after that, I can just read them off. Okay, and then term by term, we get the following. Okay. Now, what to do when the powers are both even? Well, as it turns out, gang, if you're integrating products of sines and cosines and the powers are even, there's no breaking one of them away the way that we're doing in these last couple of examples. Okay. If both of the powers are even, we have to use the half angle identities from trigonometry. Let me show you. Start with a small one. Oh, by the way, everybody, for this particular problem we just got done doing, if you were thinking that you wanted to break away one of the signs instead, then in the end, your answer would have been in terms of cosines. You should give it a shot. Give it a try. All right, but back to the even power. Suppose that we had this. Okay, so we have an even power of the sine. So that means you use the half angle identity for the sine squared, and that is equal to 1/2 1 minus the cosine of 2x. And at this point now we can read them off term by term. Set the 1/2 aside. Otherwise, the antiderivative of 1 dx is x. And of course, we have a composition here. So it's going to be the sine of 2x over 2 plus c. All right, so be careful now. Listen. When the powers of the sines and the cosines are even, there's no breaking one away like we did in the previous examples. Okay, if the powers are both even, then you have to use the half angle identities, and you may have to use them more than once. In fact, I'll do that example right here. Suppose you had sine squared of x, cosine squared of x. Okay, where both of the powers are even, that means you're going to have to use the half angle identity for both of them. Okay, now it looks like this. Okay, so that's the half angle identity for the sine squared. For the cosine squared, it's 1/2 1 plus the cosine of 2x. Okay, now we've got 1/2 here, 1/2 there, here. We can set those aside together as 1/4. And then we'll expand these two quantities. Okay, and notice that we have an even power of the cosine. Again, if you're looking at this thinking, oh, that's the sine squared, you can do that as well, right? 1 minus the cosine squared of 2x is the sine squared of 2x. There's no reason you couldn't use that. Okay, and you know what? The opportunity presented itself. I think I'm going to take it. We don't have to, but why not? Okay. Now, once again, because the power of the trig function is even, you're going to have to use the half angle identity. There's no breaking one away. So half angle identity, 1/2 1 minus the cosine of 4x. Okay. Now, at that point, you can read them off term by term. Set the 1/2 aside together with the 1/4 will give us 1/8. Otherwise, we'll have x minus the sine of 4x over 4 plus c. Okay. And maybe next time we'll make a short little video about products of tangents and secants. But for now, this is enough to get you started.